Okay, our three main big rules for electrostatics are that opposite charges attract or go towards one another. Like charges or same charges are going to repel or go away from one another. And then the things that move are only electrons. So protons do not move, only the electrons move. So with that, number one says, how does an object become negatively charged? Well, it can't gain or lose protons, it can only gain or lose electrons because those are the only things that move. Electrons are negative, so if you want to become more negative or become negatively charged, you need to gain electrons. You need more electrons. And to become positively charged, you can't gain protons because only electrons move, so that means you need to lose electrons. The difference between a conductor and an insulator: a conductor allows electrons to move within it. And an example would be metal. So in like copper, for example, or I don't know, any type of metal, the electrons can move very easily within that material. An insulator, the electrons cannot move around within it, cannot move within. So an example of this would be like rubber, plastic, styrofoam, etc. All of those would be examples of materials where you can get electrons into that material, but they can't move around within it. Grounding is to make neutral. So touching something, like a person touching it or touching that object to the ground, something is charged to make neutral, touching it to make neutral. So in the example of like the Van de Graaff generator, when we had like the big metal sphere that had a bunch of extra electrons on top, when you touched it, you got shocked because you grounded it. You took those electrons and sent them to ground. If it were positive, then you wouldn't be taking electrons to send them to ground. You'd be providing electrons from the ground to make it neutral. Whatever way the electrons need to move to make it neutral. And what does it mean if an object is neutral? It means it has the same number, so it has the same number of protons as electrons. I'll just call it P and E. It doesn't mean that there are no charges. It means there's no net charge, no total charge. I could have 1 billion protons with 1 billion electrons. That would be neutral. How does a negatively charged object interact with a neutral? So negative and neutral actually attract each other. Same with positive and neutral, those will also attract. Negative and positive will attract, negative and negative repel, positive and positive repel. So opposites attract, and also a charged and a neutral attract, which is like when I rubbed the balloon with my, got it positively or negatively charged for my hair, and then put it against the wall and it stuck. The wall was neutral, but it was still attracted to the negative object. We have a neutral electroscope, and we're just bringing near the strip but does not touch, which means the electroscope still needs to stay neutral. So you can cross off B and C because these are not neutral, right? This is all negative, this is all positive. Now here, this one is neutral, and then the electrons would leave the bottom to be going up to the top because they're attracted to this positive thing, and then that would leave the bottom negative or positive because it was neutral and the negative electrons left it. So D is the right answer. A is neutral, nothing is happening, but if you have the positive here, the electrons would want to go up and it would create this right here. 7, finding the net force. So first, let's label this A, B, C just to make our lives easier. Let's look at the last object. It feels two forces. It feels a force repelled away from C, or A and C, and then it feels a force towards B, so attracting BC. And then if I want to find the net force on C, I just know that I'm looking at these two forces, so find the force between A and C. That's going to be K, 99, charge of A, 6E negative 6, times charge of C, 9E negative 6, over the distance squared. Well, that's 0.1 and another 0.15, so that's 0.25 meters squared. And that's going to get me that the force between A and C is 7.776 newtons. And then I also need the force between B and C, so I'm just plugging into my K, Q, Q over R squared equation, where K is 99. Times now charge B, 6E negative 6, charge C, 9E negative 6. You'll notice I'm not plugging in with the negative signs on the charges because We already know what the negative signs mean, attract or repel, and it'll mess up our numbers if we plug those in. And then the distance between B and C is just the 0.15. So then that gives me that the force between B and C is 21.6 newtons. All right, and then now we're looking at net force on C. So I've got 7.776 to the right because AC are repelling, and then BC attracting is a force of 21.6 newtons. So by 21.6 newtons this way and 7.77 the other way, you just subtract. So I always do the biggest minus the smaller, and that's going to give me a net force on C of 13.824 newtons. And we always need to include direction, even though it didn't say, but it will say in the test clearly. Include direction. You have a bigger force to the left compared to the force to the right, so it'll end up going to the left. So this was your final answer. Number 8, so we start with these charges and then they come into contact in the following order. So A touches B. So when these two touch, that's -4, +1, that's a total of -3, so each has -1.5. So these would be -1.5 coulombs after. Nothing happened with these two, so I'll just pull these down, and then these are my charges now. Next step is that C and D touch each other, so we have +1 and -6, that's a total of -5, so each has -2.5. And bring the other ones down because nothing happened to A or B in this step, and we can ignore those because this is the new charge distribution. And then lastly, B and C touch, so -1.5 and -2.5, that's a total of -4, so each has -2, so -2 like this. This is the charge of all of them, and I want just on sphere C, so it's -2. Now you'll notice that it asks for the charge in coulombs. I don't need to do anything to put it into coulombs because it already was in coulombs. Now if it had been elementary charge, that's when I would multiply, put it into coulombs, but I don't need to multiply because it's already in C. Number 9, we've got 4 extra protons, meaning +4e, 2 extra protons, +2e. This is sphere A, this is sphere B, and then they come into contact, meaning they touch one another. So the charge will be evenly spread. This is a total charge of +6e, so each has +3. And then I need to figure out like which one's gaining electrons, which one's losing. So it's easy if one is positive, one is negative. That's not the case. These are both positive, and they both end up positive, which answers the first 2 questions. So they're both going to end positive. I just need to look which one got more positive. So if you look, this one was +2, now it's +3, so this one got more positive, which means that it lost an electron, or loses electrons. That means this one must have gained. And then that should make sense because yes, it is still positive, but it's less positive than before, because before I had 4 extra protons, and now I only have 3, which means you got an extra electron that would cancel that out. And then if this one is losing electrons and this one is gaining, it means they're going from this one to here because he loses and he gains. So it moves from B to A. So you should have said that A gains, B loses, so that means that it's moving from B to sphere A. And then the last part is what is the charge on sphere B in coulombs? Well, I know the charge is +3e. I need to put that into coulombs because it's not already in coulombs. That's an elementary charge, so I just multiply the +3 times the 1.6, and that's going to give me +4.8 times 10 to the -19 coulombs, I think. Let me check. Yeah. All right. Number 10, a balloon is rubbed against a sweater. Which of the following occurs? Destruction of charged particles. No. The electrons are not going to be destroyed because you rubbed a balloon against your sweater. Release of charged particles from the air in the balloon. No. Movement of negatively charged particles from a material, movement of positively charged particles. Well, we know that there is something that is transferring between the 2 objects when you do the charging by friction, the rubbing 2 materials. It's not the positively charged particles because protons don't move, only electrons do, so that makes it C. It's the movement of electrons, negatively charged particles, from one material to another. Number 11, a negatively charged rod is brought into contact with an electroscope. As the rod gives up its electrons, the number of protons remains the same because protons do not move. They are stuck in the nucleus. They can't go anywhere. Number 12, what is the charge of an object that is repelled by a negatively charged rod? Well, like charges repel, so if it's repelled by something negative, then it must also be negative because like charges repel. Like meaning the same. If something's repelled by a positive, then that means that something is positive. We've got positive 2C, negative 4C brought together in touch. So that is a total charge of negative 2C, meaning each would have negative 1C, like this. The charge of it here in coulombs after, well, negative 1C, that's easy. Now I want to know how many extra electrons that is, so that's asking for it in elementary charge. To go from C into elementary charge, you have to divide by your 1.6, etc. So I'm going to take my negative 1C, divide by the 1.6 times 10 to the negative 19th coulomb. That way when I'm dividing, I'm crossing off this coulomb and I'm left just with how many electrons that is. So negative 6.25 E 18E. And you could just say the number because technically this negative E is saying that's I have this many extra electrons. If I'm just asking how many extra electrons, this many. All right, number 14, two neutral object or materials are rubbed together. There's a transfer of electrical charge from one to the other. The net or the total electrical charge, well, your total electrical charge should remain constant because you can't create electrons. So the total charge between the two has to stay constant, and it's electrons that are transferred, not protons. So C. That's just knowing your rules. A negatively charged rod is touched to a neutral ball. After they touch and are separated, the ball is now. Well, let's say this is negative 2 and this is 0. After they touch, it'd be negative 1 and negative 1 because this one is going to give some of its electrons to this one. So after they touch, they will both be negative. So the ball will therefore be negative. Metal sphere with excess of 11 electrons and an excess of negative 15 electrons. So that's a total of negative 26, meaning that when they touch, I have negative 13 on each of them. Now that is an elementary charge because that's what it was given to me in, that's what I've been working with, but I want to know what that is in coulombs. So negative 13, to put elementary into coulombs, we're going to multiply by that factor, because now I have a C in my answer, and that's going to give me negative 2.08 E, negative 18C. Glass rod given a positive charge by rubbing it with silk. So if the rod becomes positive, that means that it loses electrons. So that's the rod that loses electrons, which means the silk is gaining electrons. I want to know about the rod, so the rod is losing electrons, C. We have an object that is positive 10E, and it is grounded, and it becomes neutral, which is the best explanation for this. So to ground means to make neutral. If it is positive and it needs, if it wants to become neutral, that means it needs extra electrons. And if it's positive 10E, then only negative 10E, 10 extra electrons, is going to make that neutral. So that means that it gains 10 electrons from the ground, A. Because that is what would make it neutral, or 0. Neutral ball touches a positively charged rod, so neutral ball, positively charged rod, let's say it's positive 2. Afterwards, it would be positive 1 and positive 1. We are looking at what the ball would do. Well, the ball started neutral and became positive, which means that it lost electrons. Wow, I did a lot of lost electrons here. If I had asked about the rod, then the rod would have gained electrons. We are drawing in the direction that the electrons would move when these two come in contact. So I still find it easier to work with the actual number. So you have positive 6, positive 2, that's a total of positive 8, meaning each has positive 4. Here, this is a total of positive 4, so each has positive 2 when they touch. Here, this is a total of 6, so positive 3 on each. Now I need to figure out which way the electrons moved. Did it go from the left sphere to the right sphere, or vice versa in each of these situations? So again, looking at the numbers helps. So this was 6 and it went to positive 4. It's still positive, but it's less positive as before, and this one is more positive. So the more positive means that it lost electrons, meaning this one gained. So it must have gone from this one to this one. Here, this one was negative and it became positive, so it's definitely more positive. Became positive, so that means this one lost, so it goes this way. This one is still positive, but it's less positive than before, because if you have positive 6, the only way you can now have positive 2 is if you had electrons come in and cancel 4 of those. And then you're left with just positive 2. Right, and then here, again, goes this way because this one became positive, which means that it lost electrons. This one gained. It became less positive. So it's always going to move from the more negative to the more positive because the electrons are going, this is the electrons move from the more negative to the more positive because the negative electrons are repelled by the negative and they're attracted to the more positive. Here, 2 positives, but the 6 was the more positive, so it went from the 2 to the 6. Here it was easy from the negative to the positive. Here this was neutral and positive 6, meaning this is again the more positive, so it has to go from the 0 to the 6. 21, how much charge does the second object need in order for the third object to be in equilibrium? You want to pay attention which one you want in equilibrium, so that's going to be C. So the forces that need to be equal if you want C in equilibrium are AC and BC, the 2 forces that are acting on C. Let's decide the sign of the charge first. So right now, we don't know what B and C are doing because we don't know what B is. But we do know that A and C are both positive, meaning they are going to repel away from each other. And then that means that the other force on C, the force between B and C, has to go to the left because you want these 2 to cancel out. If one is to the right, the other has to be the left. In this case, that is going towards B. So if they go towards each other, opposites attract, meaning this has to be negative. And then now that we've figured out the sign, now we don't worry about sign anymore. We'll just put it on our answer at the end. Now we set our forces equal. So this is going to be K, the 99, times 5. C was 10 over the whole distance from A to C squared. 3 meters and 2 meters is a distance of 5 meters squared. And then that's equal to K, charge of B, which we don't know, let's call it X, times charge of C, 10, divided by their distance squared, so 2 squared. Cross off the 99, you can cross off the 10, you've got 5 over 25 equals X over 4, because 5 squared is 25 and 2 squared is 4. And now we can just cross multiply to get the X by itself. So when you cross multiply, it's saying these 2 multiplied by each other. So 5 times 4 equals these 2 multiplied by each other, 25x. 5 times 4 is 20 equals 25x. To get x by itself, you divide the 25 over. And that's going to give me that x is 0.8 coulombs. And then we already decided that it needs to be a negative, so just remember to go back and put the negative in there. Number 22, an object has this charge when it is grounded. Remember, to ground something means to make it neutral. So if you have something that is negative and you are making it neutral, it means you're going to lose those electrons to make it go to neutral, because it already has lots of extra electrons. So I need the electrons leaving the object, because if you add more electrons in, it just becomes more and more negative. So let's cross off the electrons going into the object, because that is not going to neutralize it. So I can cross off half of them. I know that electrons are going to leave to go to ground. I just need to know how many. Now it's tempting to say, oh, this many, because this is the charge. But that's not the number of electrons. That's the that's the amount of coulombs. So we want to put this into electrons, or elementary charge. So in order to do that, we divide. And you'll see that we get to cross off the coulombs. That's going to leave me with elementary charge. When you divide, you get negative 9e. So that means that right now it has a charge of negative 9e. So to be grounded, it needs to take away those 9 electrons. So 9 electrons leave the object to go to ground. And then now it would be neutral again, E. Charged objects, it says that A attracts B. So let's say, because it's not giving me any of the actual, values, if any of the actual charge signs, if it's positive or negative. So let's say A is positive, and it attracts B. That means opposites attract, so B would have to be negative. Then if B is negative and B repels C, well, likes repels, that means C would have to be negative. And then the negative C attracts D, well, opposites attract, so D is positive. And then D repels E, likes repels, this is positive. And then lastly, E attracts F, and opposites attracts, this is negative. So then A, which we said was positive, would then attract F, which is negative, so attraction for 23. 24, we've got 4 extra protons and neutral, and I want to know after they are touched what would happen. So this would be positive 2 and positive 2 on each. This one went from neutral to positive 2, which means that it lost electrons because it became positive. This one is still positive, but it's not as positive as before, which means that it gained some electrons, in this case 2, because if you have positive 4, 1, 2, 3, 4, and you put 2 electrons in, see how those kind of cancel out, you're left with just positive 2. Okay, so then if this one is losing and this one is gaining, then it's going from this one to this one. So the sign on each would both be positive, because they end positive 2. Sphere A, we said gained. Sphere B, we said lost. And then if this one's losing, this one's gaining, it's going from B to A. And the charge on sphere B in coulombs, well, sphere B is positive 2e. I just need to put that in coulombs. You go from elementary into coulombs by multiplying. So then you get positive 3.2 times 10 to the negative 19 coulombs. Number 25, what would the distance between the second and third have to be in order for the first object to be in equilibrium? So A is the one that you need in equilibrium. So that means that forces between A and B have to equal A and C. It doesn't matter which side you put it on, right? I can say AC has to equal AB. The fact is that they have to be equal. And then we're looking for distance, so we don't have to worry about sign. So we're going to just start plugging in. So K, 99 times charge 1.92 E negative 6. Charge of C, 3 E negative 6. Again, we don't plug in the signs on the charges. Over AC. Now we don't know what AC is. Let's just call it R. So R squared equals K, 99 times the charge of A, 1.92 E negative 6, running out of room, times B, 1.92 E negative 6. Over, and then AB is just this distance 4 squared. Right, looks super nasty, but we can clean it up by crossing off 99, crossing out this 1.92 E negative 6. So I have 3E negative 6 over R squared equals, this was a 1.92 E negative 6, it got real squished in here, 4 squared is 16. And then now it's just time to cross multiply. So if you multiply these times equals these, so 1.92 E negative 6 R squared. These two multiplied together equals this one multiplied. I don't think I wrote these down. You've got the, I wrote 16 squared, but I already took care of it, so ignore the squared. That was 4 squared, which is 16. My bad. So you have 3E negative 6 times the 16. That's going to give us 4.8 E negative 5. To get R by itself, we divide this number over, running out of room, so divide the 1.92 E negative 6. That gives me that R squared is equal to 25. That's what R squared is, so I need to square root to get that R is equal to 5 meters. And now you're almost done, but that's actually not the answer, because what we just found is the R for AC. So this whole distance right here is 5 meters. But what I asked for is this question mark, this distance between B and C, but it's really easy because if this is 5 meters and this is 4, then this is just 1, you just subtract. So obviously picture not to scale because 4 and 1 would not look like the same distance. So assume that the picture is not necessarily to scale. All right, 26, we have negative 4 and negative 6 because I have 4 extra electrons and 6 extra electrons. That's a total of negative 10, so they each would have negative 5 like this. This one became, they're all started negative and they're still negative, but this one became less negative, this one became more negative. So I find it easier to think about which one became more or less positive. This one or negative, more positive or negative. This one became more negative, which means that it gained electrons. Right? First it had 4 extra, now it has 5 extra, so it just took an extra electron. This one had 6 extra, but now it only has 5 extra, so that lost electrons. this one is losing and this one is gaining, it means they're going from this one to this one. So they're going to be negative after. A is going to gain, B is going to lose. They're going to go from B to A, because this is A and this is B. And then the charge on sphere B in coulombs, well, sphere B is the negative 5e, so I need to multiply to put this into coulombs. And when you multiply, you're going to get negative 8e negative 19 coulombs, and then that would be your answer. A rod with a charge of negative 4 and a charge of negative 6 touch one another. Mark all that are correct. So if you have negative 4 and negative 6 like this, then that's a total of negative 10, so negative 5 each. Let's think about which one's losing, which one's gaining. So this one became more negative. This is super similar to one that I just did. This became more negative, which means that it gained electrons, which means this one had to lose electrons, which means that they're going from here to here. Let me draw, this one's the rod, and then this one is the sphere, just so we can just not have to like label. All right, so that means that the sphere is losing, the rod is gaining, they're going from the sphere to the rod. Sphere losing, yep, that's true. Electrons go from the sphere to the rod. Yes, we just said that. The rod loses protons, never. The rod gains protons, never. The sphere becomes neutral. No, the sphere is still negative. It's just slightly less negative than before, so it's just A and B. 28, finding the net force on the first object. So I want to find the net force, not equilibrium. Equilibrium tells me to set them equal. Net force is like adding or subtracting all the forces on the first object. So I'm going to draw in my arrows. Right now, A and B are attracting each other. And then A and C are also attracting each other like this. So then to find the net force, I need to find the force between A and B and the force between A and C. So force between A and B, 99, charge of A, but I don't plug in the negative sign out front, times charge of B, 3e negative 6, over their distance, 0.3 squared. And then that you type into your calculator, and what do you get for the force between A and B? You get 1.8 newtons. And now we need also the force between A and C, so 99, charge of A, charge of C, over the whole distance, that's 0.3 and 0.2, which is 0.5 meters squared. Plug into your calculator, you get the force between A and C is 1.944. And then now last step is just thinking through, do I add these or subtract these to get the net force on A? Well, if you look at A, the force between A and B is going to the right, and between A and C is going to the right. So if they're both in the same direction, you're just going to add these two. And that's going to get me a net force on A of 3.74 newtons to the right. Because two forces to the right means it ends up to the right. 29, a student is experimenting with different methods of charging. In his first setup, he places two touching soda cans on top of styrofoam cups, and he holds a positively charged balloon close. With the balloon still near the cans, he then separates them. So this is our picture. What is the charge on can X now, and what is the charge on can Y now? Well, let's think about if we have a positive right here, the electrons that are already within the cans want to go this way. So the electrons, the negative electrons, move to the left because they're attracted to the positive balloon. So then now you have negatives, you have extra electrons on can X, which means that can X is now negative. And then this one was neutral, but then the electrons left it, leaving can Y as positive. So now you have extra electrons on the left, and you lost electrons on the right. So that means that now this is negative, and this one is now positive. Overall, it's still the same number of electrons, right? They just went from one side to the other, so it's still between the two are neutral, but you have a negative side and a positive side. What would the charge on the first object need to be in order for the second to be in equilibrium? So that means I want B in equilibrium. This is the one. So let's figure out our sign first before we plug in. So A and B don't know what's happening, but B and C, it shows that B and C are repelling from each other. If you have a force to the left on B and you want it to be in equilibrium, that means the other force has to go the opposite direction. So that would be the AB force, meaning they go apart. And like repels, that means A must be negative. And now the forces that need to be equal, we want B, or the second object in equilibrium, so that's AB, and BC, the ones with B in it. Right, and now we plug in 99, charge of A, I don't know, let's call it X, charge of B, 4, we don't plug in the sign, distance between them is 3 squared, equals 99, charge of B, times charge of C, over the distance, 5 meters squared. Cross off the 4 and the 99, so you have X over 9 equals 8 over 25. We're going to cross multiply, so 8 times 9 equals 25 times X. 8 times 9 is, what, 72? Equals 25X. Divide the 25 over, and that's going to get us that X is 2.88 coulombs. And we had already said it needs to be negative, so we just need to make sure that's in our boxed answer. Distance between the second and the third object in order for the second object to be in equilibrium. So again, we're looking for B in equilibrium. We don't need to worry about signs here because we're not looking for charge, we're just looking for distance. So we'll set AB equal to BC again. That is 99, 18 times 10 over 2.8 squared equals BC, so 99K, Q 10 times this charge 36 over this distance, which we don't know, X squared. Cross off the 10, cross off the 99, you've got 18 over the 2.8 squared equals 36 over the X squared. Now we cross multiply, so that gives me 18X squared equals 2.8 squared times 36, I put in my calculator all at once, so I got 282.64. Alright, now still trying to get this X, so we divide the 18 over. That gives me X squared is equal to 15.68. Not telling because I want X, not X squared, so I have to get rid of the squared by taking the square root, which gives me 3.96 meters. And then sometimes we do have to subtract, so let's check. We just found the distance between B and C, which is exactly what I asked for, so just 3.96. I don't need to subtract here. That's my answer. All right, hope this was helpful. Study, do the whiteboard practice.